This set of notes is about Maxwell Boltzmann distributions. As always, you've been provided with a set of notes, or you may take your own. All right, so by definition, temperature is based on the average kinetic energy of a distribution of particles that you're measuring. And since we know that kinetic energy is 1/2 mass times velocity squared, or speed squared, we can then infer a couple different things. One, particles of the same kind or the same mass in a sample have an average speed. Okay, so if I take a whole bunch of oxygen molecules, for example, same mass, same kind, they have an average speed. The speed within that sample, though, varies. You've got some particles that are moving very, very fast. You've got some particles that are moving very, very slow, okay? But so we can describe how fast the different particles are by some kind of distribution. And it ends up being a bell-ish curve, okay? It's right skewed, so it tails off in this direction just a little bit because particles can't have a negative speed, so it gets kind of stretched out in that particular way. All right, so within my distribution then, we have some particles moving very slow, some moving very fast, and many moving sort of at these in-between speeds. All right, so those three in-between speeds, one, there is the most probable speed. Okay, in statistical terms, that would be the mode, right? And that's symbolized by the highest peak of the distribution. We have the average speed, all right? So that's our median. Okay, so that's our the middle speed, if you will, and that's right over here. Median by statistical purposes. And then, of course, we have the root mean square speed, which is the mean of all of the different particles that are part of this. So it's the speed of a particle that has kinetic energy equal to the average kinetic energy of the sample, or the mean kinetic energy of the sample. These three defined speeds are all used for slightly different purposes in terms of chemistry, but it's good to understand the difference between them. So the first thing that we need to understand here is that as temperature increases, the kinetic energy increases. All right, so as we increase that, the area under the curve for a particular set of particles stays the same. Why? Because we have the same number of particles. We're not changing that. But what happens is the peaks switch and shift slightly to the right, and that means the averages are also shifting to the right, which means that the tail also shifts to the right, and over time, if you pull that enough, your distribution flattens out, okay, as you increase the temperature. All right, so that last one was a Maxwell-Boltzmann distribution in terms of number of particles and kinetic energy. We can also graph this in terms of speed, okay, so since as temperature increases, the kinetic energy increases, that also means that the average particle increases, so particle speed increases. So that means the area under the curve still stays the same. Peak and averages shift right, the tail shifts right, and the distribution flattens. The only thing that's slightly different about this is not as right skewed as the energy distribution. So that's sort of our understanding of how the distribution shifts based on temperature. Right, the other thing we can investigate is what happens if you change the mass of particles at a particular temperature. So if we're, again, assuming a constant temperature, by definition, the kinetic energy of the particles stays the same. I can't stress that enough. At a constant temperature, the average kinetic energy of all the particles is the same. This comes up over and over and over on different tests in AP Chem. So please make sure that you understand that, right? That at a constant temperature, the average kinetic energy of all particles is the same by definition. So if we look at a graph of a Maxwell-Boltzmann distribution of energy and the number of particles, then it doesn't matter what the mass is, whether it's light like helium, medium like argon, or heavier like xenon. Again, the average kinetic energy is the same, and so the distribution for this is the same. Okay. That's not the case, though, if we talk about speed, because kinetic energy is 1/2 mass times velocity squared. So if Ke is constant and we are decreasing the mass, or we're getting lighter, then the velocity has to get bigger in order to be able to keep this constant, and vice versa. If mass increases, the velocity has to go down. And so what you end up with is a distribution that looks something like this. The average shifts to the right, the tail stretches out, and the distribution flattens. Okay, same number of particles under the curve, but you end up with a flatter distribution because of the difference in mass of these different things. So how does that work then? Okay, so the lightest particles will have the widest distribution. The smallest or the heaviest particles will have the narrowest. Another way of thinking about that is the particle speed of the heaviest is the slowest. Particle speed of the lightest is the fastest. All right, so if we compare these then, if we're talking about different temperatures, if we're talking about the kinetic energies, the kinetic energy at different temperatures will change, and you'll get a shift, right? So you change the average speed and the average kinetic energy. If you change particle mass, the average kinetic energy stays the same, but the speeds do change. Okay, so again, showing two different kinetic energy graphs here. So you'll see with temperature, the kinetic energy changes by definition. With mass, it does not change because we're at a constant temperature. All right, so why do we talk about Maxwell-Boltzmann distributions? Well, they're really important in understanding the thermodynamics and kinetics of both physical and chemical properties of matter. Later on this trimester, we will start talking about reaction rates and and things like that. And this idea of a Maxwell-Boltzmann distribution is going to become very important. In terms of states of matter, they're also important in understanding the collision forces between particles. The particles that are moving the fastest are going to have the greatest collision, and that's going to help us understand things like phase changes. Okay? That's our notes for today. Have a good one.